Hello students, welcome back to today's class on triangles, and in today's class we're going to discuss more congruency rules and some applications based on that. Right, my name is Avinash and I'm a graduate from IIT Kharagpur. Let's start today's session. So what is the first one that we have to discussed already is SSS congruence. Side congruence, and we said that when all the three sides of one triangle are equal to the other three sides of another triangle, then these two triangles are congruent. You can see that, right? So two triangles of the three sides of one triangle are respectively equal to the corresponding three sides of another triangle, and the two triangles are congruent. You can see here, right? So all these three are equal, corresponding sides are equal, then we can say that using SSS congruency, those two triangles are congruent. Congruent means they are similar, right? Corresponding angles as well as corresponding sides will be same, right? In the same way, we have also discussed about SAS congruency. What is the side angle side congruency? Two triangles are congruent if two sides, see, S and S, two sides, and the included angle, side angle, included angle of one triangle are equal to the two sides and the included angle of another triangle, right? Equal to the two sides and included angle SAS, side angle side, right, of the other triangle. You can see here, right? So side angle, this one side, this is the second side, and one angle, side angle side. That means when we have a triangle and when we say this side is similar to congruent to other triangle, the angle should also be the corresponding included angles, means the angle formed by these two sides, that is this angle. The same way it should be similar to another triangle. Then these two triangles are congruent, and if they're congruent, we can say that all the properties will be same, right? All the sides and all the angles, corresponding sides and corresponding angles will be the same. Okay. This is about SAS congruency, and then we have also discussed about ASA congruency. Once again, let us discuss about that. Two triangles are congruent if two angles, ASA, two angles and the included side, two angles and the included side of one triangle are equal to two angles, AA, and the included, it means in between two angles, one side will be there with included two angles, so that we need to take care of. Okay, let's see here. So if this triangle ABC, let's say, okay, and let us say this is the triangle PQR. We are talking about ASA. Let's say this angle and this angle are equal. Angle A and angle P are equal. Angle C and angle R are equal. Now angle and the side included side means for these two angles, the included side AC and here PQ. If these two angles and that side, angle side angle, if all these three are the same in both the triangles, then we can say that the triangles are congruent, right? We discussed about triple S, right? SSS congruency, and then we discussed about SAS, and then now we're discussing about ASA property, ASA congruency, right? So these are the different types of congruences that we can discuss in two triangles. And what else we can discuss? The next one, right? So we have a question here. Let's try to understand what is this question. L and M are two parallel lines intersected by another pair of parallel lines P and Q. Let me see where the diagram is. Yeah, here. So here you can see L, M, P, Q. I think we have in the last class we have stopped with this one, right? So L and M are two parallel lines intersected by another pair of parallel lines P and Q. So P is parallel to Q. This symbol is used for representing parallel. P is parallel to Q, and this is L is parallel to M. L is parallel. These two are parallel lines. These two are parallel lines. Okay. So now we need to show that triangle ABC is congruent to triangle CDA. ABC and CDA. So one thing I just want to tell you here, as the sides are parallel, okay, I'll tell you the solution two different methods. As these two sides are parallel and these two sides are parallel, the inside figure, the complete quadrilateral ABCD. Okay, the method 1, quadrilateral ABCD is a parallelogram. You know what is a parallelogram, right? Okay, so this is a parallelogram, and in parallelogram, opposite sides are equal. Opposite sides means BC will be equal to DA. BC will be equal to DA, right? So this is opposite. In the same way, AB will be equal to CD or DC. AB and CD. If we are considering that it is a parallelogram, it is a parallelogram. Okay, side and side are equal. This side and this side are equal, and this is the common side for all the both the triangles, right? So AC is equal to AC. So it is enough to say that using SSS congruency, these two triangles are congruent. Using side congruency, these two triangles are congruent. Okay, but now let's assume that we don't know about anything about parallelogram. We just know what are the angles. Okay, so let's try to discuss using angles. So let me erase this complete thing. All it is very simple to this, but assuming that we don't know what is a parallelogram, what are these properties, what is the sides or whatever it is, let's try to discuss with whatever we're having using the parallel lines concept. Let me write it once again. Yeah, right. So now if you consider L parallel to M, so AC will be transversal. AC will be transversal. Is it correct? Yes, that is correct. L and M are parallel, AC is a transversal, and if that is a transversal, these two angles are the same, right? Interior angles, alternate interior angles, correct? We say this as alternate interior angles, that is angle DAC. Angle DAC is equal to angle ACB. Angle DAC is equal to angle angle ACB. In the same way, there's again the same set of triangles, the same set of parallel lines and transversal. Now I can say that these two angles are also alternate interior angles, right? So that means angle BAC is equal to angle DCA. Angle DCA, right? So we have two angles, angle, and that corresponding side is same. So that is AC is common for both the triangles, right? So we can say that AC is equal to AC, correct? AC is a common side. AC is a common side. So we have a side that is common for both the triangles, and we have set of two angles, this angle and this angle, and the corresponding and the included side. Using ASA relation, right? Two angles and one side, ASA relation, we can say that these two triangles are congruent. Angle ABC and angle CDA. Angle ABC and angle CDA. These two, see, starting with A is the same starting point as in this triangle C, because of the same sides we're taking about, right? So A and C both are same, so A should be matching with C, right? And we discussed here AC or angle DAC, angle AC, then you can compare the sides. Okay, so from A to B, C to D here. From A we are coming to B, here from C to D. A to B, C to D. And ABC, CDA. ABC, CDA. So we can say that these two triangles are congruent. Whenever you're writing congruency, the order of the numbers, order of the letters ABC, CDA are very important. Because if you are doing any mistake in that, the way of representation, it will be entirely a wrong concept. Clear? Alright, so this is how you can try to prove that they are congruent. Let's move for one more. AAS congruency. The name itself says an angle, and side. We also discussed ASA. What is the difference between ASA and the AAS? ASA is two angles and the included side. Two angles and the included side, like this. If this is a triangle, this one angle, and we're talking about this included side. But now we are not considering that condition. Two triangles are congruent if any two pairs of angles are angles and one pair of corresponding sides are equal. Any two pairs of angles and one side is equal. AAS, angle, side. It may be ASA or may not be. We don't care about that. but one angle and another side. If these three are similar to another triangle, then we can say that these two triangles are congruent. These two triangles are congruent. Okay, let's try to understand this one. So if you take about a triangle ABC and a triangle PQR, triangle ABC and triangle PQR, two pairs of angles and one pair of corresponding sides. Okay, so let's say this angle is equal to this angle is equal to this angle, and now it's not the included side, that is with ASA. It can be any other side. You can say that this side and this side are equal. It is enough to say that it is an AAS congruence. Angle side congruence. You can say that it is following AAS congruence, and in AAS congruence also these two triangles are the same. We can say that they are congruent. All the corresponding sides and angles will be same, right? Okay, moving forward for the next question, right? So what's the next one? RHS congruence. It is very important. Out of all these, RHS will be very important. We have a lot of geometrical applications based on this one in the higher classes, right? What is that? In two right angle triangles. Right angle triangles. Do you know what is right angle triangle? This is the right angle triangle. Okay, in two right angle triangles, the hypotenuse, this is the hypotenuse, the longest side is hypotenuse. Okay, hypotenuse and one side of one triangle, let's say this side. Okay, one side of one triangle are equal to the hypotenuse and one side of another triangle. See, right angle, the hypotenuse and one side. Why only hypotenuse and one side were considered? Because in right angle, by default, in both the triangles, one angle will be 90 degrees. This angle is 90 degrees. You know that. Okay, so this angle is 90 degrees. So even though you don't mention, if there are two right angle triangles anywhere in the universe, anywhere in the world, one right angle here and one right angle somewhere in America, but still they have one common property that the right angle, this angle is 90 degrees. So even though it is not mentioned, that angle is already incongruent. Okay, that is already in same. So it is enough to mention any two, one hypotenuse and one side. It is enough because already angle is already there, right? So in two right angle triangles, the hypotenuse and one side of one triangle, hypotenuse and one side of another triangle, if these two are equal, we can say that the triangles are congruent. That means all the angles and all the sides will be same. Okay. Moving ahead about this RHS congruence, let's try to apply more about this one. So what is that? Pythagoras theorem is a very important theorem. You might have already learned in some other chapter, but once again, let's try to discuss what is Pythagoras. It's a very important topic. Okay. In a right angle triangle, the square of hypotenuse, okay, in a right angle triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides of triangle. The square of the hypotenuse is equal to the sum of the squares of other two sides of the triangle. Okay, let's try to understand this one. For example, I have ABC as a right angle triangle, right angled at B. Right angled at B, the square of the hypotenuse AC square. Square of the hypotenuse, this is the hypotenuse. Always in a right angle triangle, the longest side or the side opposite to right angle. The side opposite right angle, that is the hypotenuse. So square of the hypotenuse square is equal to sum of, so that means addition of two terms, squares of other two sides. One side is AB square, other side is BC square. Other side is BC square. AC square is equal to AB square plus BC square. Okay, AC square, which is the hypotenuse, is equal to AB square plus BC square. So this is how these sides of right angle triangle are connected to each other. This theorem is called a Pythagoras theorem, and it is a very important theorem in many geometrical applications, in many algebraical applications. We use this relation whenever we say right angle triangle. Okay, let's try to understand more about that one. So which of the following is a Pythagorean triplets? Which of the following are Pythagorean triplets? That means Pythagorean triplet, that means all the three should follow a right angle triangle where hypotenuse square is equal to side square plus side square. Okay, So you can see here, out of 4, 12, 13, which is the largest side? Out of 4, 12, 13, which is the largest side? Largest is 13 square, correct? So 13 square should be equal to 12 square plus 4 square. So we need to see whether it is correct or wrong. If not, then we'll try to see what can be done. 13 square, let me calculate 13 into 13. 13, so there is a 9, 3 1 3, 3 1 3, 1. So 9, 6, 1. 9, 6, 1. So that becomes a 169 is equal to 12 square. 12 square, 12 into 12, 2 2s are 4, 2 2s are 2 1s 2. 2 1s 2, 1 1, so 144. 144 plus 4 square 16. Plus 4 square is 16, right? So 169 is equal to 150 or 160. 160, these are not equal, so we can say that these three numbers are not the Pythagorean triplet. These sides are not Pythagorean triplet. Let's check about this one. 7, 15 and 17. Let me check 17 square. 17 into 17, if I'm not wrong, it may be 289. 7 is 49, 7 1 7, 11, then 17, 9, 8, 289. Okay, 15 square, I remember it is 225. And 7 square, I remember it is 49. So let us add this to 14, 4, 5, 6, 7, 274, and that is a 289. Once again, please cross check that. Okay, so these are not the Pythagorean triplets. I'll give you one more example here. Let's try to discuss with the 5, 12, 13. Let's try to discuss with 5, 12, 13. Let me check that once again. 9, 5, 14, 4, 5, 6, 7, 274, 17, 17, right? 289. Okay. So 13 square, just now we discussed 169. 5 square, I know it is 25. Plus 12 square, I know it is 144. So 25 plus 144 is equal to 169. Is that correct? 144 and 25. 9, 6, 1. Correct. Okay. So 5, 12, 13. This follows a Pythagorean triplet. This follows a Pythagorean triplet. Okay, so even I think 17 and 15, let me calculate 289 minus 225. 289 minus 225, it should be 4, and this should be 44, 64. No, 6. Okay, there is some other triplet, maybe 815 or something like that, whatever it is. Okay, so this does not follow Pythagorean triplet. Understand? Okay, let's try to move ahead. Okay, so we have a question here on the topic of congruence of triangles. AD is an altitude of an isosceles triangle ABC in which AB is equal to AC. Show that AD bisects BC. So we have a triangle. Once again, let's try to understand the question more carefully. AD is an altitude of an isosceles triangle ABC in which AB is equal to AC. AB is equal to AC. AB is equal to AC. Show that AD bisects BC. AD bisects BC, right? So now, carefully observe, this is an altitude. Do you know what is an altitude? Altitude means height. And whenever we say altitude or height, the angle it is making with the base is 90 degrees. So this is 90 degrees angle. Even this is 90 degrees angle. Okay, these two are 90 degrees. Right, slowly we can compare something. So we have a side which are equal, we have an angle which is equal, and even the AD is a corresponding side. But the question is, the point we need to show that it is AD bisects BC. Okay, see here. We have a side, right, in the triangle AD, in the triangle ABD and triangle ACD. Triangle ABD and triangle ACD, if you carefully observe, AB, the side AB is equal to AC, it is already given that, right? It is an isosceles triangle. AB is equal to AC, it is already mentioned to us. The next one, we have, see in this triangle it is an hypotenuse. If you carefully observe, this is the hypotenuse of both the triangles. Hypotenuse is equal and, okay, and one side which is nothing but AD. So AD is equal to AD, so it is enough with using RHS congruency. Using RHS congruency, these two triangles are congruent. Which two triangles? Triangle ABD is congruent to triangle ACD. Triangle ABD is congruent to triangle ACD. Now, as these two sides are, these two triangles are congruent, we can say that BD, the corresponding side BD is equal to DC. The corresponding side BD is equal to DC. BD is equal to DC, right? So now with this we can say that this triangle, these two triangles are congruent, and AD bisects BC. AD bisects BC. Okay, so till here the part is clear. Now let's move towards the other question, the same thing, that is the next one is AD bisects angle A. AD bisects angle A. Now I told you triangle ABD is congruent to triangle ACD. Triangle ABD is congruent to triangle ACD, right? So when these two triangles are congruent, even the corresponding angles, angle BAD is equal to angle CAD. So these two are equal. So we can say that AD is the angular bisector. We can say that AD bisects angle A. Bisect means dividing into two parts. If this is x degrees, this is also x, so the complete angle is at 2x. The complete angle is 2x, which is divided by x and x. Okay, so we can say that AD, it is the angular bisector, or we can say that AD bisects angle A. Right? So these are very basic questions. I'll give you one or two more questions so that you can try to do that. ABCD is a quadrilateral. Okay, we don't know which quadrilateral it is. Let me draw any quadrilateral. Okay, this is one type of quadrilateral. It can be anything. Okay. ABCD is a quadrilateral in which AB is equal to, let's say this is ABCD. AB is equal to BC. AB is equal to BC, and AD is equal to CD. AD is equal to CD. Right? Show that BD bisects both the angle ABC and ADC. BD bisects both the angles, angle ABC, angle AB, that means this one and this one should be equal, and triangle ADC, this angle and this angle should be same. So we need to prove that. Okay, I'm leaving that concept for you because this is a simple two triangles. One side is equal, the other side is equal. So try to compare, try to bring more relations about the angles so that you can understand how these two triangles are congruent, and from there you can say that the angles are also equal. Okay, so you can take that as a take home assignment. We'll take one more question. In a right angle triangle, prove that the line segment joining the midpoint of the hypotenuse to the opposite vertex is half the hypotenuse. Okay, I'm leaving this for you. In a right angle triangle, prove that the line segment joining the midpoint of hypotenuse to the opposite vertex. Opposite vertex means the right angle vertex. Okay, so this length is equal to half the hypotenuse. This should be equal to half the hypotenuse, right? There is small information given, it is already midpoint, so these two sides are equal already. Okay, so from there you can try to bring more relations. You need to prove that for example, this is x and this is y, right? So y should be equal to x, or you can say that y 2y is equal to x. Okay, or y is equal to half of hypotenuse. We need to show that it is half of x, right? So use the different congruences and try to bring that relations. Okay, so in the same way we have a couple of more questions on the same thing, so which we can discuss in the next class. Prove that the medians of an equal triangle are equal. Median, so let me recall that. So this is one median. Median always passes to the midpoint of the opposite side. Median always passes to the midpoint of the opposite side. So if you say this is ABC, let us take this point as D. As it is median, I can say that BD is already equal to DC, right? Let me draw one more. So here BE, let us say, so AE is equal to EC. Okay, so these two are with midpoints because median, but it is already given equilateral. So if whatever you do, already the sides are equal, right? So AC is equal to BC. AC is equal to BC. Already this side and this side are equal, and in that exactly the midpoints, that means AE, EC, even these two sides are equal. As the complete everything is same, we can say that AE is equal to EC is equal to CD is equal to BD. All these half sides are equal. Okay, Now I'm not going to do completely, but you can compare. There are two different triangles. So now we can compare with triangle ADC and triangle ADC and triangle EBC. Triangle EBC. Triangle ADC and triangle EBC, and you can see carefully. Angle C is common for both the triangles. Angle C is equal to angle C. We have enough cases, enough conditions. Angles are equal, sides are equal, sides are equal. It is more than enough to say that these two triangles are congruent, but try to arrange them properly, whichever the properties SSA, SSS or SSA or ASA, whatever it is, try to bring it properly. And finally, you need to show that medians are equal. That means AD is a median which should be equal to BE. So you need to compare these two triangles, make them those two are congruent, and show that AD is equal to B. If these two are done, if these triangles are congruent, we can say that those two are equal. And if these two are equal, we can say that similarly, the other third median is also equal to the same, right? So in that way, you can try to discuss all the congruence properties behind this one. So one more question we are having, so which you can try once again. ABC is a right triangle and right angle at B. So this is ABC, right? Such that angle BCA, let us say this is X, or angle C, whatever it is. Angle BCA is twice of angle BAC. Let's take it as Y. But one thing you need to understand, this is already an right angle triangle. Okay, this angle is 90 degrees, and here, if one is X, the other will be 2X, right? Such that BCAX is equal to twice of BAC. Is equal to twice of BAC, right? So you can say that X equal to 2Y or 2Y equal to X, whatever the relations are. I'm not going to do that. Very easy. Try to understand the question. I can say here one relation, that is X plus Y plus 90 is equal to 180, because sum of the angles of triangles is 180. From there you can bring X plus Y is equal to 90, right? So you can also bring Y is equal to 90 minus X, X minus 90, and given one is the twice of other. So basically you will get the angles. One will be 30 and the other will be 60, okay? 30 degrees and 60 degrees. But still there are some properties you need to understand and you need to apply properly, so that you can get that those two different triangles are there, and from there you need to show that AC will be equal to twice of BC, right? So that's all for today's class. I hope you understood all these questions, right? A couple of questions I gave you as a homework. Please try to solve that clearly. Okay, so thank you so much, students. Stay tuned to get the next lecture. Thank you.
Hello everyone. So now we'll be discussing about universal law of gravitation. Okay, so my name is Shashan Reddy. I'm a graduate from IIT Dhanbad. Let's go into the class. Right, so look at this. Have you any time heard this story? At least watched it? It'll again come, it'll again play, don't worry. So it's starting again. An apple falls on a person sitting under a tree, and that person starts to think about something. You know that story very well. Yes or no? Who is that? That is Newton. Newton sitting under a tree and an apple falls down. So Newton starts thinking, why is the apple only falling down? Why is the apple not going up? Right, and then he comes to the answer of gravitation. Now this is just a story. No one knows whether it is actually true or not. What we know for sure is Newton gave us the universal law of gravitation. This is just a story to entertain what? To entertain Newton and his concepts. Okay, good. So gravitational force by the earth, this is something we know. And what do we know? All objects on earth. When I say all objects, it could be us, it could be this pen, it could be this remote, it could be this TV, it could be anything. The wall, buildings, animals, birds, anything. All objects on earth fall towards the ground because of the gravitational force exerted on them by earth. Earth applies the gravitational force on them. Yes? Yes. And on any object, I told you, on every object, gravitational force by earth is vertically downwards. You can see there's a person jumping down, and when he jumps, He falls down but not goes up. Why? Because of gravitational force by the earth. Okay, that's fine. There is gravitational force by the earth on the objects situated on the earth, obviously. But again, we also know that moon revolves around the earth. Moon revolves around the earth, and in the last class, circular motion, we learnt about centripetal force. So which force is responsible for the circular motion of moon around the earth? Which force is responsible for the circular motion of moon around the earth, or which force acts as the centripetal force in this case? And we discussed about that there is only one possible force or only one possible object that can exert the force, that is force on the moon by the earth, and it will be towards the earth. Yes or no? I'll write it as force on moon by what? By earth. So earth exerts a force on the moon. Earth exerts a force on the moon, and because of that force, moon revolves around the earth. The question is, what is that force? It should be some type of force, some kind of force. It should have a name. What is that force? And that is also gravitational force. That is also what? Gravitational force. So earth also exerts gravitational force on the moon. On the moon, and moon is not inside the earth, far away from earth. Right? Good. So based on that, we come to a statement called as universal law of gravitation. Now what exactly is this? What exactly it is? Let's understand through a few examples. We'll take earth and moon itself as an example. Earth and moon. Okay. So here on the moon, we understood that earth exerts a force on the moon. FME, force on moon by earth. Newton's third law, remember that. Now according to Newton's third law, F12 is equal to minus F21. For every action there is an equal and opposite reaction. So if there is a force on the moon by the earth, then there should also be a reaction, that is force on earth by the moon, which would be what? In this way. Force on earth by the moon is equal to negative of force on moon by the earth. Negative will mean opposite sign. So here this is force on earth by the moon. Now this is gravitational force. So what is this force then? This force will also be gravitational. So here if you think about this is the first clue that we have. Earth exerts a force on moon, that is completely fine, but moon also exerts a force on earth. Look at that, moon also exerts a force on earth, gravitational force. So gravitational force is not only the property of earth, no. Other objects also can exert gravitational force. For example, moon. We have other examples also, in fact. I'll give you another example. We can take earth and sun as an example. Earth revolves around the sun, yes or no? Earth revolves around the sun. So who applies a force on earth? Sun applies a force on earth. Force on earth by the sun. That means, according to Newton's third law, there will be a force on the sun. By whom? By earth. Understand that. On earth, sun is applying a force. Because of that force, earth is revolving around the sun. But at the same time, on sun also, earth applies a force. And which force is that? That will obviously be gravitational force. So on the earth, who is applying gravitational force now? Sun is applying gravitational force. So the examples that we have learnt about until now, we learnt that gravitational force is applied or exerted by earth, by moon, now the sun also. Do we have other examples? Yes, we have. Other planets also revolve around the sun. Mercury, Mars, Jupiter, Saturn, all of them revolve around the sun. That means there is gravitational force between the sun and that planet also. So, from that we can come to a conclusion that gravitational force is applied by all the objects, not only Earth, by all the objects. Okay. Now for us it's very easy to tell, but think about it during the time of Newton when there was nothing else and Newton had to tell all of them. Okay, let's go into that. So what is that law and all? Let's look into it. So it's just an explanation which we have already seen, right? So let me skip that. So the universal law of gravitation. So what did Newton tell? And it was very brave of him to give this law. And what is law? Law is a rule. It means he told that, there is a rule, a universal rule. Universal will mean throughout the universe. And that rule is applicable throughout the universe. So Newton was a person who was sitting on the earth and he gave a rule that is valid throughout the universe. That's how brave it is and that's how wonderful science is. So what is that rule? He told that if you take any two objects, one of mass small m and the other of mass capital M. I'm just showing you, they can be of different masses. Small m and capital M to show that they are of different masses. You can take them as M1 and M2 also. It's up to you. You can take any different mass. Okay. I'll take it as small m and capital M. Now when I say any two objects, it can be this remote. One object can be this remote, one object can be me. Or one object can be this pen and the other object can be this remote. One object can be this pen and the other object can be this screen, anything. Okay, so any two objects. Even a very small microorganism also which you cannot see. Anything that has mass. An apple also. Okay, so he told that between any two objects there will be a gravitational force. Which force? Gravitational force. It is attractive, both of them try to attract each other. It is not repulsive. Gravitational force is always attractive. First point that he gave. Right, and he told that between any two objects in the complete universe. And then he told that he also gave us the formula. Or more properly speaking, he gave us the terms or the quantities on which the force depends. He told that the force will depend on mass of both the objects. Or if I combine them, I can say it depends or it is directly proportional to the product of both the masses and is inversely proportional to the square of distance between them. So if the distance between them, and you have to take the distance from one center to the other center, not from one end to end, it should be center to center distance. So Newton told that between any two objects there is gravitational force, it is attractive and it depends or it is directly proportional to the product of the masses of both the objects as well as inversely proportional to square of the distance between the two objects. Now some of you might be getting confused. Sir, what is this proportionality? We have never seen that. What is that? What does that mean? I'll explain proportionality in a bit. Okay, so when it comes to proportionality will show its a mathematical concept, but let me give you a brief idea. Let's say if I have an equation y is equal to x square by z. Y is equal to x square by z. Now you tell me here, if x increases, what happens to y? Will y increase or will y decrease? What will happen? Think and tell. If x increases, what will happen to y? Think of it. Yeah, everyone? If x increases, y will also increase. I'll just give you an example. You can think of this. I'll say x is equal to 2. Then what is y is equal to x square, 2 square, 4 by z. Then I'll take x is equal to 3. Then what is y equal to 3 square, 9 by z. So obviously if you compare 4 by z and 9 by z, which is greater? 9 by z is greater. So x is increasing from 2 to 3 and y is also increasing from 4 by z to 9 by z. Understood? Clear? So here one increases, the other automatically increases. And so for this type of dependency, we say that they are directly proportional. And you should not forget the power. So what we say is y is proportional to the square of x. So proportionality, this is called as what? Proportionality, proportional symbol, proportionality symbol. So y is directly proportional to the square of x. You have to take the power also. So it shows that if x increases, y increases. Directly proportional will mean if one quantity increases, the other quantity increases. And for directly proportional, both in numerator or you can say both in denominator. I mean, for example, if I look at y and x, y is in the numerator, x is also in the numerator. That's what I'm talking about. Okay? Okay, that is one type of relation, one type of dependency. Now comes the other one. What happens if z increases? What happens if z increases? Let me take an example. If z increases. So first of all, you tell me, if denominator increases, does the value increase or decrease? If the denominator increases, does the value increase or decrease? Just take a very simple example here. 1 by 2 is equal to how much? Half. 0.5 in decimals. 1 by 4 is equal to how much? 0.25 in decimals. Now look at the denominators. 2 to 4. Did it increase? Denominator has increased from 2 to 4. But what about the complete value, the fraction? Think of it in decimals. It is decreasing from 0.5 to 2.5. Yes or no? 2 to 4 increasing. You can say 2 to 4 it is increasing. But 0.5 to 0.25, what's happening? It is decreasing. So if one is in the numerator, the other is in the denominator. See, y in the numerator, z in the denominator. Then what happens? What happens is, if z increases, then the other one decreases. Or if z decreases, y increases. That's the beauty. Understood? Clear? Yes. So we go into the example. The same example, you can take it there. Okay. So let me just skip that part and write it down. We call it as inversely proportional. Different proportionality. You have to know the terms. Directly proportional, one increases, the other it decreases. Direct. Inversely, ulta. Right, inversely proportional. So we say y is inversely proportional to z. And as you can see, z denominator, y numerator. So one in numerator and the other in denominator. And the other in denominator. That's how it will work. Understood? So a bit of maths, but understand the proportionality properly. Two terms. Directly proportional, inversely proportional. Directly proportional will mean if x increases, y increases. Like both of them will increase. Inversely proportional, one increases, the other decreases. To identify them, both of them in the numerator, directly proportional. Both of them in denominator, directly proportional. But one in numerator and the other in denominator, inversely proportional. Okay? Got it? Okay, let's continue. So again, coming back to our Newton's law. Okay, universal law of gravitation. We'll go into the complete statement. But again, what did Newton tell? He told that between any two objects, remote and pen also, between any two objects there will be a gravitational force which is attractive, and that force, it depends on what? It depends on mass as well as the distance between the objects. How? It is directly proportional to the masses, or you can say the product of their masses, and is inversely proportional to the distance or the square of distance between the objects. That means here, this implies that directly proportional. So if small m increases or capital M increases, then what happens? The force increases, directly proportional. That is the reason. But here what does that mean? If distance increases, then force decreases. D increases, then force decreases. Inversely proportional. Got it? Simple explanation. Wonderful. Chalo. So here, look at the points. Every point here is important. Every point is beautiful. Beautiful and very important. Every object in the universe, understand the weight behind the words. Every object. When I say every object, it could be, again, me, the pen, the remote, the air molecules, the air particles, star, very, very far away stars, galaxies, or even a microorganism. So objects as big as a star, or objects as small as a microorganism. You can take any object, it's up to you. Every object in the universe, not earth, universe, attracts every other object in the universe with a force which is, I'll go into that, but again coming back, it attracts every other object. That means I'm standing here, but I'm attracting you now. I'm applying a force on you. You might be in different cities, you might be in different countries, different states, doesn't matter. I'm attracting you. I am an object, you are an object, so I'm attracting you, and you are attracting me. I'm attracting stars, I'm attracting sun, I'm attracting the moon, I'm attracting Jupiter, I'm attracting other galaxies also. Understood? That's the weight behind that statement, and it's true. It has been proven true. So every object in the universe attracts every other object in the universe with a force. What is this force? Gravitational force. Okay. It attracts, not repels, it always attracts. That force is proportional to the product of their masses and inversely proportional to the square of the distance between them. Okay, and how does it act? And it acts along the line joining the centers of the two objects. You have to join the center of the two objects, and then it will act along that line. You can see that here. This I can say F12, and this you can say F21. Understood? So this, you have to know each and every point in this. Okay, so understand each and every word, each and every sentence of this, and also you have to remember it. Yeah, you have to understand and as well as remember this. Got it? And who gave this law? Newton gave this law. Newton gave us many laws, right? Newton gave this law. That's why Newton is so admired. Got it? Take them down. Take the points down. I've shown you in terms of points 1, 2, 3. Okay. But yeah, normally speaking, it would be a complete, one full sentence. But again, if you write in points, it is easier to understand and remember as well. And diagram is also important, by the way. Very simple diagram. Don't neglect it. Wherever it is possible, you have to draw a diagram. Because it shows things clearly. That is the reason. Okay. Good. Let's continue. So, what did we get? We have to derive a formula. Let's derive the formula. For formula, there should be an equal to sign. But as of now, we have proportionality sign. So, we need a formula. We need what? We need a formula. And what is the distance, everyone? The distance, again, let me repeat. The distance is the distance between the centers, not anywhere else. So between the centers, D is the distance between the center of the objects. So we got that the gravitational force is proportional to the product of their masses, right? You multiply them, so proportionality. And is inversely proportional to the square of the distance. So once you get all the proportionality conditions, so this is all of it. So once you get all of them, what you will do is you just directly multiply them. And as you say, if F is proportional to, you write it down and multiply these two. That's it. Multiply them directly. So when you multiply them, what will remain? M into 1, mm. Right, so mm by d square. You just combine them and write it down. That's it. Okay. Now, so you have combined all the factors into one. Okay, but is this an equation? Because see, in equation we need an equal to sign. But here what do we have? We have a proportionality sign, not an equal to. So how do you get that equal to? What we do is another mathematical thing. Whenever you get the final formula, the final thing, in terms of a proportionality sign, what you will do is, you will replace the proportionality sign with what? With an equal to and a constant. Look at this. This is replaced. That's it. It's a mathematical thing. You do what? You replace the proportionality sign with an equal to and a constant, and then write down the others in the same way. That's it. And see, you got an equal to sign. So you got a formula. So what is that? G. That's very important. G is just a constant. Okay. So normally it is what? Here it is the constant. We call it as constant of proportionality. That is the common name in all the cases. But here for G particularly, because we are talking about universal gravitational law, universal law of gravitation, what we say is, we call it using a special name. You know what is that name? Universal gravitational constant. Universal gravitational constant. The name is very important, by the way. This name is very important. Very simple, but it's very important. What is capital G? Capital G is just a constant. And its name is universal gravitational constant. Okay? Simple. So these are some simple 4 steps that you have to show to get this formula. Okay, so we got a formula for gravitational force. So what is the formula? Again, the formula is simple. You have to learn it by heart. Simple, learn it by heart. Okay. F, the gravitational force between two objects, is equal to capital G, capital M, small m upon d square. Again, you have to understand each and every term. What is capital G? The universal gravitational constant. What are capital M and small m? The masses of both the objects. What is D? D is the distance between the centers of the two objects. Clear? Good. Okay, that's fine. That's what we have done here. Okay, and what is G? G is the universal gravitational constant. Remember the formula. Got it? So use this formula. Start practicing as many problems as you can. So once you keep practicing, then you will understand. Okay, so you got a basic idea of the gravitational law, right? Then start practicing, then you'll understand things much more clearly. Do not wait, okay sir, I didn't understand everything properly. Don't wait, just start practicing. Then with practice, you'll understand it much more clearly, much more better. So start practicing, okay? So let's go into a simple question then. We'll also start practicing. Find the SI unit of universal gravitational constant. How do we do this? Very simple, let me do it. So what is the formula? We start from the formula F is equal to capital G, capital M, small m upon d square. We need the unit of what? Capital G. So let's get the formula for capital G from this. How? We'll first take d square to that side. What will happen? F d square is equal to capital G, capital M, small m. Then I'll take the capital M and small m to the other side. Here it is multiplication, there it becomes division. It becomes f d square by capital M small m is equal to capital G. So just interchange. So we got capital G as f d square by capital M small m. Got it? Simple. 2 steps and we get it. Just rearrange the terms. Okay? Good. Now look at this. We have to get the SI unit. So how do you get the SI units? Very simple here. What you can do is write down the SI unit, the terms that you have. That is for F. What is the SI unit? F is for force. So for force, the SI unit is Newton. The symbol is capital N. Now what about D? D is distance. And for distance, the SI unit is meter, small m. Then for capital M and small m, what are they? They are masses. For mass, the SI unit is kilogram. So just substitute all of them in that equation and you will get the SI unit of capital G. So let's do that. In place of F, you have Newton, capital N. Then in place of D, D is distance, meter. D square, so meter square upon capital M, small m, both of them, the units are what? Kilogram, kg into kg. Now I'll write this as Newton meter square divided by kilogram into kilogram, so kilogram square. Okay, kilogram square. It's not equal to, by the way, I just use an arrow. The SI unit will be this. And why are we doing this question first? Because for any new quantity that you come across, any new term, it is important to know the units. And trust me, many forget the units in this case. Many people forget the units. So please do this, practice this and remember the SI units of capital G. Just do it 2-3 times and automatically you will remember it. Even if you want to forget it, you will not forget. Okay? Good? Easy? Yes. So universal gravitational constant, that's what we are talking about. So G is the constant of proportionality in the formula for gravitational force between two objects. We got this formula. Now its value, as I told, it's a constant. So constant will mean it will have only one value. Yes. So what is its value? How can we find it? Now there are experiments to do it. So people have done experiments and from experiments we got the value of capital G. For now we are not going into the experiment part. What we will do is we'll just remember the value. So what is the value of capital G? It is 6.67 into 10 power minus 11 Newton meter square upon kilogram square. Negative power will mean division, denominator. So Newton meter square per kilogram square. Very important. That value is very important. So for this complete chapter, the gravitation chapter, this value will be very important. So 7 stars, 7-star hotel. Right? So please do remember that. 6.67 into 10 power minus 11. Now let us try to understand how huge that value is. What is the value of capital G? 6.67 into 10 power minus 11 Newton meter square upon kilogram square. Now look at 10 power minus 11. What does minus mean? What does negative power mean? It means division. That becomes 6.67 divided by 10 power 11 Newton meter square per kilogram square. Now look at 10 power 11. The power 11, what does that mean? It means in this case for 10, it is just 11 zeros. Now is this a very small value or is this a very huge value? What do you think? Capital G, the value of capital G, is it very small or is it very huge? Yeah, look at that. And 6.67 is divided with this. In that case, it will be very small value. Right? In fact, if I write it down, I have to be careful when I count the zeros. With 10 zeros here. I mean, let me count them again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 0 point, see that, how small it is, 0.000, 000, 0.0000667. It's very difficult to count the zeros. That's how small it is. That's how small it is. Okay. It's important to understand the value. Okay. Now, so why is that important? Because I told you that, or the law tells that between every two objects there is gravitational force. So here, between the remote and between the pen, there is gravitational force. But why can't we feel it? Why can't we feel it? The answer lies in the value of this capital G. Because see, it's so small, the value itself is so small that if the mass of object is less, then gravitational force will be very, very, very less. And we can't feel it. And we can't feel it. It will be there very, very, very small. Because ultimately, what is gravitational force? The formula is capital G, capital M, small m upon d square. So if capital G is small, then automatically the force will be small. Okay, that is the reason. Okay, we'll also go into an example, but I don't think we'll have much time. We'll do that in the next class. Do not worry. Okay, and here the important point is the value of G remains constant throughout the universe, wherever you go. On Earth, on Moon, near the Sun, outside our solar system, in our galaxy, other galaxies, near other stars, wherever you go, the value of capital G remains the same. That is the reason why it's called as universal. It is constant throughout the universe at any point in space and at any point in time, past, future, present, doesn't matter. And hence it is called as universal gravitational constant. So this is also important. So a very simple question will come. Why is capital G called as universal gravitational constant? The simple answer is this. Okay. Got it? So the value of G was found out by Henry Cavendish, again a name of a scientist. He has done the experiment and he has found it. Okay. So I think that's it for today. We'll end it here. But